So once again, thank you for having me for this presentation, and I'll mainly be talking about our recent work at that got into Soda this year. It's about quantum advantage via solving multivariate polynomials, and it's with a few of my co-authors from pretty much, I think, yeah, all over the place. Um, so let me just get into the crux of what is the problem that we are solving here, and where is the quantum advantage, so as to speak, coming from. So to begin with, just to give a brief primer so that everybody is on the same page, whenever I'm talking about multivariate polynomials, I'm talking about, so you can imagine a system of polynomials, each of which is like non-linear. So it's a non-linear system of multivariate polynomials. Think degree 2, degree 3, or any degree D in general. And usually there will be two parameters, m and n, where n will be the number of variables that you pick. So here in this try example that I've given, it's like n equals 3, and you have two equations. And again, the problem is the usual thing. I give you a system of polynomials and I ask you, hey, can you find me a solution to the system, right? So in this try example, it has two solutions over F2, and you can generalize this problem over any finite field. Doesn't need to be over FQ. FQ is the most standard one, but over higher order fields is also completely fine. And when we talk about these polynomial systems in the context of cryptography, mostly we are talking about uniform polynomial system, uniform random systems of polynomial, by which I mean look at every monomial. So if you think of a quadratic system, let's say a quadratic polynomial, for example, so you will have coefficients that look like, let's say x1, x2, x1, x2, x1, x3, and so on. So for every such monomial, you toss a coin at random and choose your coefficient accordingly. So if you're over F2, you toss a coin. If it's 0, you include that in. If it's 1, you don't. Sorry, if it's 0, you don't include it in. If it's 1, you include it in. Right? So that's a uniform random polynomial. And usually, like the problem that we are asked to solve is something that looks like this. So here, this is an example of a degree 2 polynomial because it's just easy to write down. So I just stuck to a quadratic polynomial. It's saying if I give you the system of the coefficients that are these AIs, these are the matrices of the coefficients, and I give you the evaluations, right? And let's say I give you k many of these evaluations, and can you find me an x prime such that x prime transpose AIX for all of these i's matches the solutions that I provided you. And it's this problem has been studied for, I think, decades now. It was introduced in early 80s or late 70s, so it's been around for a while. It's well studied, and solving such a system of nonlinear polynomial system is known to be NP complete within. So there are, of course, there are parameters where it becomes easier. If I give you too many equations, then it will become easier. If I give you very few equations, then again it will be easy. But there is a decent parameter range where it's actually hard to solve. It's NP complete, and even the average case problem is known to be hard to it's believed to be hard. There are no tractable algorithms for it that we know so far. Um, and the other thing why particularly this polynomial or like particularly this family of problems is that this problem has been fundamental to post-quantum cryptography recently, particularly the quadratic problem. Like the MQ problem has been used in a lot of multivariate public key primitives. We have signature schemes that are based on this family of assumptions. In fact, a few of them have also made its way to the NIST standardization, where there is a whole effort going on to standardize a few candidates for the post-quantum security, and it includes some constructions that are based on these problems. Right? So that's the motivation why we should care about the system of polynomials. And again, as I said, a random system of polynomial is fairly well studied, and there have been a lot of cryptanalysis done to it. So I think people believe its hardness without much concern. But the thing to note here that there's a slight caveat here, and the caveat is that existing constructions that use polynomials under the hood, they do not really use random polynomials, because what happens is random polynomials end up having no structure that you can actually utilize for, let's say, public key primitives. So at the end of the day, you have to use a much stronger assumption by relying on some structured polynomials. And what sort of structure are we looking at? I'm going to give a brief example in the next few slides so that we get a flavor of what happens here, right? So these are structured systems and not truly random polynomials. And what we have learned so far in the cryptanalysis land is the more structure you push into a problem, the more susceptible it becomes to algebraic attacks, right? For example, let's say we know like Shor's algorithm that breaks factoring discrete log. It relies on the periodicity of the group structure. So if you have such strong structure, maybe you can come up with an algorithm to break problems like this. And in fact, what we have seen is that there have been some problems that have been broken. And in fact, this example that I've put out there, Rainbow, it was one of the candidates for NIST signatures posted, I think, in 2022. And then there was a classical attack on this problem, not even a quantum attack. So what this is telling us is, again, Rainbow was also, as I said, like all other constructions, relied on some structured polynomial under the hood. And basically, the attack obliterated that polynomial completely. So what this is telling us is that although there are candidates that we keep using and we believe are potentially post-quantum secure, but there is probably a gap here, right? And what might be slightly more concerning is that the common consensus, or shouldn't say consensus, the common belief in our community is that if there is a multivariate based construction that is not broken classically, then that's likely to be quantum safe as well. So in that sense, there is no gap between there's no quantum classical gap in, let's say, a system of polynomials, is what the common, uh, widely believed thing is in the community. So to give some flavor and context into what sort of polynomials we are looking at when I call a structured system, I'll just give you a very brief overview on a very popular construction based on multivariate cryptography. And this is called the oil and vinegar scheme. It's a signature scheme that was proposed, I think, late 90s. And this is actually one of the very, I think, currently unbroken signature schemes out there that is very fairly well known. And what does this look like? So it's a quadratic system. So think about a system of polynomials, which has like two pairs of variables, each of length k, let's say. So you have total of two times k many variables. And let's say you have some k many degree two equations, where the coefficient matrix looks like this, which is like it has a zero on the upper diagonal. Um, and let's say A1, A2, A3 are just random matrices everywhere else, right? So in a simplified setting where if you just imagine this X that I've written there to be just X1, X2, what this essentially translates into is that there are no quadratic terms with respect to X1. So there you can have quadratic terms with respect to X2, you can have cross terms X1, X2, but there won't be like X1 will never interact with itself. Right. So in particular, if you observe here, what's happening is if you assign just random values to x2, right? You just guess. You don't care what it is. You assign random values to x2, you end up with a system of linear polynomials now. So this particular system of polynomials is trivially broken. Like if I give you like k equations and two k variables, what are you going to do? You're just going to randomly guess x2s. Pick whatever you want. Now you're left behind with a linear system of k equations and k variables. This you can clearly solve by Gaussian elimination. So this polynomial system is clearly broken. Like not even quantum, it's classically broken. Right? So this is no good. But what you can do is, or what people do is, you assume some linear transformation T on these 2k many variables, and your goal is to mask this clearly broken matrix A with these linear transformation. Right. So now you don't give out these A matrices out in the clear, you give out these T transpose A T matrices out of the clear. So you can think about your secret being A's and T's, and what you're making public is T transpose A T. So basically, in some way, you're using this T to mask the structural vulnerability of A under the hood. Right. And yeah, so basically at a very high level, and this is not just oil and vinegar, this happens in I would say not exactly like this, but fairly in the same, it has the same flavor and pretty much every construction based on polynomial system that we know so far, where the goal is to start with an easy to solve quadratic system, which is clearly broken, and then mask it with some appropriate linear constraints. Like this is the general recipe to build anything from based on multivariate polynomials. And this again has
Sorry,
been secure. Yeah.
uh, sorry to interrupt, but I was just a bit
Mhm.
curious. Why is it called oil and vinegar? Is there like
Ah,
some reason?
yeah. Okay, so this is this is interesting. So it's called oil and vinegar because I think the observation was you call one set of variables the oil variables and the other set of variables the vinegar variables, and the logic is that two different oils don't mix with each other. So the x1 part of it are called the oil variables, the other part is called vinegar variables. Like that was the logic behind this naming.
I see. Okay, thank you.
Yeah. So yeah, and the whole point is that you don't want these oil variables to mix with each other and get this quadratic term. Then we just don't know how to use the system. So that's what the authors named it. So yeah, so oil and vinegar is the most popular one. In fact, in last year, oil and vinegar was uh, selected as one of the candidates for a digital signature scheme. It's like one of the alternates to the lattice-based constructions that we that's most popularly used. So right, so what do we see so far? What we see so far is that we have a fairly widely used system of, let's say, a fairly widely used problem that is considered to be hard, and it's even standardized as a post-quantum secure assumption. But at the crux, what's happening here is that this belief in post-quantum security is probably just because there is a lack of quantum algorithms to analyze such problems, right? The major quantum breakthrough that we've seen was probably Shor and a few other things that we have so far. But when it comes to polynomial systems, we probably just do not have enough quantum tools to analyze what is going on here under the hood. So in this particular work, what we want to do is we want to challenge this very belief, right? And we want to basically set out a flag over there saying, hey, be a little bit more skeptical. Maybe there are some natural families of polynomials that you can break using a quantum attack. And specifically, the question we ask is there a family of polynomials that is probably classically hard, which is fine, but quantum broken? So is there a gap for any family of polynomials? Is there such a gap? And as of now, or at least before our work, we did not know of any family of polynomials where such a gap existed. So either we have polynomial systems that are completely secure all the way through, or there are polynomial families that have been shown to be classically broken. So there was nothing that was classically secure but quantum broken, right? So this is the problem that this is the question that we ask, and specifically as a one slide conclusion of what we're able to achieve is that we present a candidate distribution of polynomial systems over F2. The F2 is not important. You can do it over any field FQ. That is plausibly classically hard. And yet we give an explicit quantum algorithm that solves it in polynomial time. And why I say plausibly classically hard is because, of course, there is no way for us to prove that uh, any family of polynomials or any problem is classically hard unless we actually end up proving like something like P naught equals to NP or something. So that's why I only say plausibly classically hard, and that's because we tried all of the state of the art ways to attack these polynomial systems. We also came up with some new tools, like not new tools, like some new algorithms specific for our system. And again, we could show that none of them really work. So that's pretty much all that we can hope to have when it comes to guaranteeing classical hardness. But yes, we give an explicit quantum algorithm that I'll discuss shortly, and it works in polynomial time, of course. And what's interesting about our algorithm and this algorithmic framework is that existing quantum algorithms that like broke these algebraic problems relied on periodicity, right? Because most of them are like based out of Shor's. So it relies on periodicity. However, multivariate polynomials do not have any such periodic structure. And of course, like we don't find any. So what we're doing is exploiting something completely different here compared to what has been done so far. And in particular, we exploit the Fourier spectrum that is created by the distribution of the roots of the polynomials. If I give you a polynomial system and the roots and you look at the roots, you do a QFT on it and go into the Fourier domain. You then analyze what that Fourier spectrum looks like, and it turns out that there are some patterns that you can find over there, which I'll talk about soon. Uh, all right. So
So,
now that yeah.
so I had a small question.
Mhm,
So, with the like plausibly classically hard part, so is there
mhm.
any underlying assumption based on which you can say, okay, if this assumption is true, then it is like classically hard, or
No.
are we conjecturing that
Uh,
it is
mhm.
classically hard, or is it
Right.
some sort
So
of
uh, right. Good question. So what we are showing is that we are giving you a family of polynomials, and we cannot reduce it to any other, let's say, widely believed or standard hard problem. We just conjecture that this problem itself is classically hard because we threw a bunch of attacks at it, pretty much all the tools that we know so far, and none of them seem to be working, right?
okay?
And and to give you one more, like a little bit more context, so I don't think that we can expect to have such a reduction, because what will happen is most of the widely known problems, multivariate based problems, will probably reduce are probably all of those random multivariate systems that I spoke about. So it is highly unlikely that you can reduce one of these structured problems that to one of the standard problems and also give a quantum algorithm, because those problems are extremely unstructured. So we just don't know how to handle, let's say, a random system at all so far.
No,
Right?
is there like a quick follow-up? So is there like a range
Mhm.
of parameters for which it turns from being easy for both quantum and classical, then maybe it becomes stays easy for quantum but hard for classical, and then also becomes hard for quantum in some regime for the same problem? Is that the case? Or
Right. That's a really good question. So yes, there will be a parameter regime where the problem is going to be just easy throughout. And that parameter regime is, so this is generally true for any system of multivariate polynomials. So if you take a polynomial system over, let's say, n variables, and let's say it's degree d, and if I give you what do you call, yeah, if I give you omega of n to the d many equations, so at least n to the d many equations, then you can just break it, like, all the way through. Similarly, the other way around is also true. If I give you a system of equations with um, n variables and n to the 1 over d many equations, so extremely few equations, but like with a factor of 1 over d to it, then even that system is easily broken. So so n and d are very important, the number of equations and the number of degree. That's basically the threshold where we are at. So when we use this for cryptography or the interesting parameter regime is always the, let's just talk about quadratic for specific numbers. It's usually between the square root n to n square regime. So you want something like n to the 0.5 plus epsilon up to n to the n square minus epsilon. So in that regime is where it's interesting. And what we are showing here is that this particular problem is quantum easy all the way through. Like, doesn't matter what the number of equations are, it's quantum easy. The classical hardness result, those barriers, of course, still hold. Like wherever it's expected to be classically easy, it's classically easy, right?
well, thank you.
Yeah. All right. So now that I've given I believe I've given some context, let's just directly dive into the polynomial system that we have looked into, the polynomial system that we've come up with. So
I'm
the
sorry,
polynomial system, yeah.
just one quick clarification. So does
Mhm.
the polynomial like does it do your results hold only for a specific field, or is it essentially true for uh, like the hardness results?
Right. So our result in our paper, we do it for F2 just for simplicity, but you can do it for any field, like any FQ will
Oh, I
work.
see. Oh, I see.
Yeah. Yeah. But yeah, we just do it for F2 because it's easy to handle, but you can do for anything. So our polynomial system has the same structure as what I said in the oil and vinegar thing. You will have two families of equations. One will be an easy or completely broken higher degree system, and then you will have a linear constraint on top of it. Right? So you start with something that looks like this. Right? So you start with think about a bunch of variables x1 through xn plus 1 through x2n, so all the way up to xn cube, right? So here I'm just looking at n cube is a specific example just for concreteness, but that is flexible. I'll talk about that later. So think about all of these variables and now split all of these variables into chunks of size n. So you have n square many such chunks, and I'll treat all of these n squared, all of these chunks as input to one polynomial, right? So now you'll have n square many polynomials, and then P1 interacts with x1 through xn, P2 interacts with x plus 1 to x2n, and so on, right? So basically what I created is n square many polynomials, each having disjoint variables, right? And now you can think about these polynomials as random degree d greater than equals to 3. So this is the limit that we have so far, where we get the separation result for cubic and above. So our quantum algorithm works even for quadratic. So our quantum algorithm works all the way through. The problem is the system of polynomials that I'll describe is is actually is also classically easy. So there is no classical hardness there as well. So that's why the separation result is only meaningful for cubic and above. And why it is easy for why is it easy for quadratic is it's a subtle technical thing, and I'm happy to go into a discussion of that if we have time or if somebody's interested. But for the time being, so imagine starting with n square many cubic or above polynomials, each of them having disjoint variables, right? So now you can like this is just very easy to see. If I give you the system of polynomials and I tell you and I let's just solve and I ask you, hey, can you find me pre-images corresponding to let's say the all zero system solution, and then it's easy, right? Because every polynomial has completely independent random variables. So you just guess at every point and you'll just find a solution trivially. So this system of polynomials by itself is not interesting at all, right? So with this, what I'm going to add is I'm going to add a linear constraint. And this linear constraint is going to be a parity check matrix for a Reed-Solomon code. So I am going to go into a brief background of these codes and Reed-Solomon codes in the next slide. But just bear with me for now. You can just imagine it to be, just think about stack all the variables one on top of the other into this vector x. So this x is, think about it as an n cube length vector, and just hit it on the left with a matrix, a random matrix, not a random matrix, a particular matrix H that, and you just so that it satisfies this constraint that H times X is equals to 0. So this is a specific linear constraint that I want on these variables. Now, this matrix H is not a random matrix. It's a specific parity check matrix for Reed-Solomon code. So to help a little bit here, let me just give you a brief. I'll just take a 2-minute detour into Reed-Solomon codes and the parity check matrix. So here, think about uh, a linear code as basically when I say a linear code of length m and rank k, just think about a k-dimensional subspace of fq to the m, right? So for example, it's essentially like saying you pick, and the way you generate this code is you pick a random vector of length k, and you just multiply it with a matrix G, which is like m times k dimensions, right? So what happens is it'll map the C that will come as an output is a member of fq to the m, and it lies in this k dimensional subspace, right? And G is typically called the generator matrix of this code. And so you repeat it for all X, and whatever C's you get is essentially what the code word is, and G is the generator matrix of this particular code. And the other property here is that for every such G, you will have a matrix H that will annihilate this G. So the left null space spanner of this G, that's H, and you'll always find such a matrix H with the dimensions that I've just mentioned, right? So it's M minus the rank of G times M, and such that this is zero. And this matrix is called the parity check matrix of the code C, right? And then essentially the point is, if I give you any code word that is generated by G, and if I hit it with H, it is going to annihilate it. So it's going to H of every code word is going to be zero. That's the point. And of course, every linear code has a corresponding dual code, which is typically shown as the C perp that is generated using H. So G and H both form their own code, both generate their own code words, which are dual of each other. Right? So if I give you any code word from C, any code word from C perp, and take the inner product, they're going to become 0. That's what the parity check matrix or the linear code does. And usually a lot of these linear codes come up with an error correction property. And by an error correction property, I mean the following. One of them is what we call list decoding. So what is list decoding? It's saying that if I give you any x, let's say any vector x in the image space of the code, and I give you some error bound e, so a code is called list decodable error correcting code if there exists an efficient algorithm that takes as input this x comma e and will output all the code words c that are within this Hamming weight from your target point. So think about any algorithm, deterministic algorithm takes as input a target point x, some error that you specified, and will spit out all the code words within that Hamming ball of that target point. So we do have such code words, and one such code word is a Reed-Solomon code, which is probably the most versatile and widely used code out there. And that has very good list decoding properties with appropriate parameters, right? So I'm not going to go into what these parameters are, but there are codes. Basically, all we need to take from here is that Reed-Solomon code is a code where such a decoding property exists, where if I give you an error-induced code word, you can retrieve the code word from it, or a list of code words from it, right? And it turns out that the dual, if you take the Reed-Solomon code generating matrix and look at its dual, that's also a variant of the Reed-Solomon code, which is a very useful property here, which is called a generalized Reed-Solomon code. But again, that's not going to be very crucial for the context of this talk. It's just like what I'm trying to say is that the dual of a Reed-Solomon code will also be a Reed-Solomon code. And it's very easy to describe. So with this context, just going back to the constraints that we have. So basically what I'm saying is, to get these linear constraints, what you're going to do is imagine a Reed-Solomon code matrix. Think about it as G. H is basically going to be the parity check matrix for that Reed-Solomon code, and you just plug in this particular constraint over there, right? And what I want to say is that X is going to be a dual Reed-Solomon code word. So at the end of the day, the bottom line is I'm going to feed you a system of polynomials where I'm saying the following two things: that give me an x that satisfies these degree d higher degree polynomial system and is also a dual Reed-Solomon code word simultaneously. Right. So this is the problem that we'll try to solve here. Right. So I think here this would probably be a good place for me to just ask, like, any questions so far? Is the problem the polynomial system? Does it make sense?
I just wanted to quickly check. So not an
Mhm.
error correction in a while. So H and H bar are related by, I guess, H bar transpose H is 0, something like this. Is that?
No. So sorry about that. Yeah. So basically, again, for there's a slight technicality over here. So our polynomials are over F2, but the code
Mhm.
word that we want to use is over an extension field. It's over F sub 2 to the n. So if you just look at the matrix is over a field extension. So
Mhm.
now
Mhm.
the over so H is your parity check matrix. So think about any matrix over. So it's a linear constraint over F sub 2 to the n.
Mhm.
But because we are going to treat everything as an F2 vector, we have to transform this H into this linear constraint into an F2 linear constraint. Now that can be done by like standard techniques. So that's why that H bar just comes in for, that's just a technicality that's telling you we are working over the extension field, but interpret everything as a constraint over F2, not over F2 to the n.
Okay, sorry. I thought H bar was the dual or something. Okay, sorry. It's just basically a
Yeah.
repackaging
So
of. Okay, got
yeah, H itself is the parity check matrix for this dual Reed-Solomon code, and then H bar
okay,
is just the packaging it into F2.
got it.
Right?
Sorry. I got it.
Yeah.
Thanks.
Mhm. Right. So you have the system of polynomials, and again, what we show here is that we show that known classical attacks fail, and that we can actually come up with an explicit quantum attack on this family of polynomials. And in this talk, I'm not going to go into details about the classical attacks, what we did, and because it's again the answer to all of them are we tried the state of the art things and none of them worked, and we tried some other new things and they did not work. So the main focus from now on will just be on the quantum algorithm, right? So good. So our quantum algorithm basically follows this Yamakawa-Zhandry framework, which was also actually, I think, even earlier adapted by Regev in his quantum reduction between SIS and LWE, if I'm correct, or SIS and SVP, one of those reductions. It's so what is this? What does this framework involve? So step one, you set up this quantum state. You set up this quantum state phi, and just think about it as some superposition of a bunch of some superposition of qubits with appropriate weights. So here I'm just naming them as vx's, right? So your phi is just summation of vx of the quantum state x.
Sorry,
And
sorry, but
so yeah.
can we quickly interrupt before you go into the details? Is there
Mhm.
is there any sense in which one could maybe give like an oracle separation? Like, is there an oracle way of instantiating the problem? Like for example, in Yamakawa-Zhandry, right? Like they could do it like they give an explicit bound, right, in the random oracle model for at
Mhm.
least the classical case, right? So that gives us something stronger than saying that existing techniques don't work. Do you think something like this could also be done for your problem setting? Or
Maybe you could potentially give something from a if you just interpret this as an oracle problem, but the way we look at it is actually the other way around. So our result, you can interpret our result as a real world instantiation of the random oracle in Yamakawa-Zhandry. So you take the random oracle, and what we are saying is you can actually instantiate it as a degree 3 polynomial, and then
right?
you can recover the exact same result, but without any oracles. So you can definitely go back in the other direction, maybe not use a random oracle all the way and some intermediate oracle. I wouldn't be surprised if you can actually do that. But yeah, we haven't thought about that.
Hmm, I see.
Right?
Okay, thank you.
Yeah. So, okay, so the Yamakawa-Zhandry framework is basically saying you first set up the state phi, which is a superposition with some appropriate weights, Vx's. And at the same time, you set up another state psi, which is a superposition of these y qubits with some other weight vector, some weight thing that you just denote with w's, right? And the goal in this framework is to come up with this coordinate-wise product, right? Where we want to extract out this quantum state, which is the superposition of x's with the weight, where the weights is like the is vx times wx. So it's the coordinate-wise product of v and w. Now, why is this non-trivial? Is you cannot just take the tensor and hope to get this particular state, because if you just take the tensor, you're going to have like tons of these cross products. Like Vx and Wy, you're going to have these tons of these cross products, and we do not want that. So just taking a tensor does not really work. So the whole challenge or the whole goal of this framework is to start from this phi and psi and somehow extract out this coordinate-wise product, right? And why is this like, why bother about this coordinate-wise product? Why is it important is the following. So in our case, think about this, the first quantum state phi, as a superposition of all of these code words, these dual Reed-Solomon code words that I began with, right? So the X was a Reed-Solomon code word, so take all the uniform superpositions, right? And the way you take it is you just pick these VXs so that it's 1 over square root the size of the code word if it belongs to the code word, otherwise you just set it to be 0, right? So this set phi here, this quantum state phi here is just a uniform superposition of the dual Reed-Solomon code words. So this you can set up uh, efficiently and fairly easily. So this is the first step, first thing that you can do. The second thing that you can do is you can set up these states called like psi i's, which is imagine every polynomial that you picked and basically set up a uniform superposition of the roots of that polynomial, right? So your these weight vectors will be 1 over the size of the root set if it's a root, otherwise just pick it to be 0, right? So the psi I is a uniform superposition of all the roots of the polynomial pi. And then you just have to take another step where you tensor all of these psi i's together to get your effective psi, right? So this psi is basically a uniform superposition of all of these n square many polynomials simultaneously. And again, this state also can be set up fairly easily. And now observe the following. So we picked X to be a dual Reed-Solomon code word. So by definition, Vx is equals to 0 if and only if this linear constraint is satisfied, right? So that's by the definition of how we set things up. So now, if so, Vx will be non-zero when x is a dual Reed-Solomon code word, and Wx will be non-zero when x is also a solution to the higher degree systems, right? So Vx and Wx will be simultaneously non-zero only when x satisfies both of these constraints at the same time, right? So if I can extract out this particular superposition, then and we measure, we'll only be measuring, it's guaranteed that we'll only be measuring those x's for which v and w both are non-zero. And that will happen when x satisfies both of the constraints that we want. So that's why this is our goal. If you can extract out this particular quantum state for us, we can then just simply measure the state and we'll get a particular solution out for us. Right? So this is why looking at this coordinate-wise product is relevant and is super important. So going into a little bit more specific on how you can do it is, so this is what you will do. So you start with your phi and psi, as I already mentioned, and then you take the QFT. So phi hat and psi hat are the standard usual QFTs of these two quantum states. And then you just compute the tensor, the usual tensor as we know of. And so you can think about the weights of in the Fourier domain to be v hat and w hat, as we usually do. So then your tensor will be v hat times w hat times x and y. Right? So this is the state in the Fourier domain. And then the first step that you usually do is you take an addition unitary and then add the two states together and store it in the, let's say, the second part of the register, right? So it's x, and you can just convert. You add this unitary on phi hat and psi hat, and you can get x plus y. Right? This can be done easily, and now you just hope that some way, by again, I'm not specify how, if you can somehow uncompute the first register, right? If you can somehow uncompute the first register and just kill off that x in any particular way, however you want, if you can do that and you extract this particular state, which is like 0 and x plus y, then I would say that we've gotten somewhere, because now what you can do is you can use like standard quantum operations. Like, for example, you can use convolution to convert this into this v hat star, w hat star state. This is just like a standard convolution result. And this state is turns out to be like exactly equal to the QFT of the coordinate-wise product that we are looking for. Right? So if you can uncompute and get and extract that x out of this state completely, then we are pretty much there from what we want, right? And now once you have this QFT, you do the inverse, basically invert this QFT and you have the desired state. And then you measure and you get what you want. So this is effectively what is happening. This is the entire algorithm. The main question here is, how do you uncompute this x? Right? This seems to be the non-trivial part of this algorithm. And essentially the question is this. Like, I give you this add phi hat psi hat, which looks like this, which is like x and x plus y. How do you like uncompute this x? So the first observation or the first result here that needs to be noted is that if you start from x, so we started with x as the dual Reed-Solomon code word. So after taking QFT, it turns out that x becomes a Reed-Solomon code word. And in fact, the state phi that we started with, which was a uniform superposition over the dual Reed-Solomon code word, upon taking the QFT, phi hat becomes a uniform superposition over the Reed-Solomon code word space. So this is a very useful result that we have. So for the first observation, x actually becomes a Reed-Solomon code word. So the next thing is, okay, so what we do is, the idea is to interpret this y as a noise. Just think about it as a noise. X is a Reed-Solomon code word, y is the noise that gets added to the Reed-Solomon code word, and then you try to decode this noise out of it. So if I give you, so basically feed x plus y into a unitary, that will spit out, let's say, x for you, that extracts out x for you, and then you subtract that x from the first register. And that's how we hope to uncompute this state, right? And in particular, like, you can interpret that as something like this. So you add a decode unitary, which is basically, think about this decode as some efficient algorithm that can run on x plus y. It will extract out x from you, and then you can just subtract x from the first register, this decode from the first register. And that's how we hope to uncompute, right? And now, of course, as I said, the C-perf in the perpendicular space turns out to be a Reed-Solomon code, and we hope to use the Reed-Solomon list decoding algorithm under the hood to enable this operation. So, and again, what we want to achieve that for most of these x's and y's, you can actually decode. Like there will be a decoding error. You cannot, of course, decode for all of them, but you hope that for almost all of them, you can actually decode and you extract out the state x completely from it, right? So this is now the challenge is, okay, you can't, of course, you cannot do it for any y. Like any distribution of y, you cannot hope to extract out x from x plus y. In general, x plus y perfectly hides x. So you definitely need some specific distribution of y. So there are two questions to be solved here. First, you need to know what distributions of y can a Reed-Solomon list decoding algorithm handle. And the next question you have to, so where does this y come from? This y comes from our polynomials, right? So y are the roots to the polynomials. So the next thing that you need to know is what is this distribution of y that the polynomials induce? So, do those two things align with each other? Right? So that is the main technical crux of uncomputing this x. So before diving there, let me just give you like a consolidated algorithm. The quantum algorithm just does the following. As I
So
said, set up a,
before,
yeah.
it's just on the previous slide. So what
Mhm.
is so I've forgotten Yamakawa-Zhandry now, but how is the distribution over y for Yamakawa-Zhandry? Is there like some
Yeah,
intuition? Because like just
yeah,
from what you're saying, it sounds like it shouldn't be random. But for
yeah.
Yamakawa-Zhandry, I would imagine that it is fully random in some way. But I'm
Right.
missing something. Can you help?
Yeah, yeah. Definitely. So if you like be patient for like two slides, that's going to pop up. I'm going to talk about the
Oh, okay.
Yamakawa-Zhandry
Sorry.
distribution as well. Yeah, yeah, no worries. All good. Yeah. So yeah, so basically the question now is about the distribution of this y, right? And okay, so before that, let's consolidate the algorithm. The algorithm is basically what I'm saying is take a uniform superposition over the code words that I began with, take a uniform superposition over the polynomials. So these are your two states phi and psi. Then do the QFT on both of them and take the tensors. That's the rightmost part of step two. Do the QFTs of the two quantum states, take the tensor, do the unitary addition, do the decoding that I said, and then just invert the QFT. That's all you need to do, and then you just measure the second register, and that will give you the desired result. This is essentially what the algorithm is. But the main question at hand is the following, right? So you want to make sure that for most of the, and when I say most here, it's like an extremely overwhelming fraction of these x comma y you should be able to decode, right? So the question here is one, what error distributions can you uniquely decode out of? Because that's important. You have to decode. And the second question is the error distribution that is induced by the roots of these multivariate polynomials compatible with this distribution? So this is the main question at hand, right? So it turns out that Yamakawa-Zhandry did follow this same approach, and they used a random oracle. So if you think about Yamakawa-Zhandry's approach was also starting with this disjoint, so evaluating random oracles at disjoint variables, and then combining all of them together with a Reed-Solomon code. So it's the exact same. It's a very similar paradigm in which we are working, except we have polynomials. They had random oracles, and random
Uh,
oracles.
so yeah, I had a
Uh,
small question.
yeah.
So we haven't like decided on what the polynomial actually is, right? Yet, or have we?
We have, right? So it's just a random degree D polynomial. It's not a structured polynomial, just a random degree D
Okay, it's
polynomial.
a random polynomial. Okay, okay. Because I was just wondering, like if we know the distribution of y, then we can like choose an appropriate polynomial. Right?
Sorry, if you know the distribution of what, can you?
If we knew the distribution of y that can be decoded,
Uh-huh.
sorry, from which we can decode x,
Mhm.
then we can choose a polynomial whose roots are following the same distribution.
Right. Good point. So, okay. So, what you're saying is if we know what Reed-Solomon code can handle, what error distributions, then we can just tailor our polynomial system to fit into
Right, right.
that to generate that distribution, right? That's an interesting idea. The thing is, and it can be looked at. I just have not thought about it from that perspective, and I'll tell you why. Because um, this distribution is actually induced by the Fourier in the Fourier spectrum of these roots. So it's actually
Right.
not very clean to directly analyze. Like, I don't know how to reverse engineer this. Like, if you give me a particular distribution and you tell me, hey, can you generate a system of polynomials that will induce this distribution in the Fourier spectrum? It's just not clear to me how I would go about doing it. But
Hmm.
that's definitely an interesting thing to look at. So here what we do is we just start with this random polynomial and we show what distribution is actually induced.
Okay, right.
So
Yeah.
just to follow up, do we have like a full characterization in some sense of all distributions over Y that Reed-Solomon can handle? Or is it
Uh,
something you have to do like case by case?
we have a fairly good characterization in the sense it's related to the minimum distance. So
Right.
basically, if you have a code word of length, let's say n, then anything, let's say, for example, anything that's more than half of them corrupted. Like, so if you have like half, so imagine everything is over F2. If you have more than like half plus epsilon many corruptions, then there's just no hope. Just cannot decode anything. But you can go arbitrarily close to half using, I think, using using list decoding, you can go arbitrarily close to half, but then um, I think the it is you can decode up to 1 minus k over m fraction of errors, right? So if k is the rank, m is the length of the code, then you can decode up to 1 minus k over m fraction. I think that's the pretty strong, I think pretty tight bound for each Solomon code. That's so that field is actually fairly very clearly understood. There's been a lot of work over there, and I don't think there's anything open there. So we know very well what error distribution, and it's not the distribution of the error that matters. It's the number of points at which you corrupt. So it's basically the Hamming weight that the entire error will have is what is important there. Okay, so moving on, yeah. So as I was saying, Yamakawa-Zhandry also did the same thing, but they use similar thing, but they use random oracles. Now it turns out that random oracles are much more cleaner objects than polynomials in the sense they're like true random generators, right? So in Yamakawa-Zhandry, what they show is that their error looks like the following. So they also have this burst pattern or they also have this blockwise structure on the errors. And for them, the error every block. So it's like when I say EI, I mean every n length block EI either was all zeros with probability half or was uniform random over everything else. Right. So the weight at everything else was like 1 over 2 to the n minus 1 over 2 to the n minus 1. Right. So it's like uniform over everything else. So basically negligible weight over everything else and just zero everywhere else. And exactly half at zero. Right? So this was what the distribution induced by random oracles was, right? And Yamakawa-Zhandry showed that if this is the error distribution, then you can actually decode from, then you can decode then you can basically use this error distribution to decode Reed-Solomon codes. What we show is that because unfortunately polynomials do not satisfy this property, and in fact it's far far from this. Like, so you will not get this uniform distribution over all non-zero points in case of a polynomial. But what we show is that we extend that result of Yamakawa-Zhandry, and what we show is that you don't really need the error distribution in order to decode. You don't really need the error distribution to be uniform over everything else. What you basically need is you need a weight of half around at zero. You still need that. But what you need is you just want the mass to be negligible everywhere else. So it doesn't need to be exactly uniform. You just don't want it to be heavily distributed over any other point. That's all the things you need. And here, of course, this half is, I would say, is arbitrary, and that pops up because we were dealing with random polynomials. It's okay as long as it's like 1 over c, right? So if you can have a distribution where your errors are uh, your EIs are 0 with probability 1 over c for some constant c, and everywhere else it's negligible. Then is that in that case as well, this particular result works, right? So this is the error distribution that we show you can actually use to decode from. And so this was the first result that hey, you can generalize the Yamakawa-Zhandry thing to for a wider class of these error distributions. And then the next question was, does the root set of the polynomial actually satisfy this property, right? Because that is important. If the polynomial root set does not satisfy this property, then there is just no point. So to go a little bit into that, So what does, again, rehashing what I already mentioned. So what does this state psi look like? It's basically a superposition. It's summation of wi y, right? And this wi is nothing but 1 over the size of the root set if it's a root, otherwise it's 0. So when we do the QFT on top of that, the psi hat looks like this. Like, so wi hat is basically you have this normalization factor, and then you get the usual term that pops up. And so in the Fourier domain, what is the probability of observing uh, a particular point y? It's nothing but the expected weight of expected value of wi hat, right? So it's basically wi hat square. That is the expected weight that you hope to. That's the distribution that you hope this expect this y's to follow. And now, if you observe, what is the expectation of wi hat 0? So look at this wi hat y expression and just feed 0 in place of y, right? So this -1 to the y inner product of y and z just disappears. That's just 1. So you're just left with summation over z, wiz, right? And now wiz is either 1 over the square root, the size of the root set, or is 0. So this is basically like an indicator variable that's counting the number of entries in the root set. So when you basically solve this out, you will have a size of the root set term in the numerator, and you'll have a square root set r times in the square root of the size of the root set in the denominator. And then when you take the square, you're basically just left with expectation of the root set of a random polynomial times this normalization factor, right? And 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 this is just like some standard counting argument. If I give you just one polynomial, a random any degree d polynomial, and ask you what is the expected number of roots, it's exactly half of the total points, right? Because you fix any particular point, and then with probability half one, you can basically match all the coefficients correctly. So your size of the root set is always 2 to the n minus 1. So then when you do this, you end up with you look at you. It turns out that the mass at 0 is still exactly half in case of a polynomial, right? Or in other words, in simpler terms, you can just attribute it to the one-wise independence of any polynomial system that just gives this half property. So this resolves the first problem. So we see that the weight at 0 for a random polynomial is actually half. To show the second property, it's a little bit more involved, but at the very high level, what you can show is that if you have random polynomials, that then the weight at these non-zero points is actually upper bounded by 2 to the square, like minus n over 2. So it's like it's a fairly negligible term, and that's all we wanted, right? We wanted that the weight at the non-zero points is negligible everywhere, which is what happens. And the main thing that achieves this result is the observation that any degree greater than 2 polynomial is 2 wise independent. So 2 wise independence is actually good enough to give this property. So what this is actually saying is all you need is a system of polynomials that is 2 wise independent. If you can come up with a system of polynomials that's 2 wise independent, you can use a quantum algorithm on that. Right? So specifically, any 2 wise independent distribution on polynomials will work for our quantum algorithm. Right? So just to summarize all of this and to conclude, again, as I said, prior to this work, no polynomial time algorithm was known against any multivariate system. What we explicitly show is that if you have a system that is a variable disjoint constraints on higher degree polynomials, in fact, not even higher degree polynomials, all we want is a 2-wise independent distribution over the polynomial system. And there's this caveat here on shift invariant, but that's we don't know how to get rid of it. It's a technical property that we need from to get one of the lemmas to hold, but effectively it's almost 2-wise independent. So in model, you can think about it as a 2-wise independent family of polynomials, and if they're tied up together with a Reed-Solomon code, then that gives you a system, an explicit system of polynomials that is quantum broken but is plausibly classically secure, right? And now this actually, okay, to end my talk, and when it comes to some future directions, one interesting problem here is, of course, you can think about decoding using some other approach. You don't need to use a Reed-Solomon decoder per se, or you don't need to use an error correcting code decoder. If you use something else, and you might be able to expand this particular approach for other polynomial systems. So, for example, one explicit thing that I can tell you is one crucial property that we have that we need is that these polynomials that we have are remain variable disjoint, right? So we have only one equation per polynomial. So can you extend that further? So let's say you have a bunch of polynomials, which is the probably a little bit more natural distribution where you have a bunch of polynomials working on the same variables. And so can you extend it to that setting? So can you actually decode from or decode or basically have a quantum algorithm for that family? And that's something that we are still trying to explore and we do not know yet. So yeah, thank you so much. That will be all that I have to say today. And I'm happy to take questions.